All right, question number 3, 2018 AP Physics 1. You have a disk spins about axle at its center. Student experimental reveals that disk is spinning. Friction between axle and disk exert constant torque on the disk. So it's going to slow down the disk. Right? So this, I'll say this is friction. So it's going to slow down the spinning, right? At t equals 0, disk has initial clockwise angular velocity omega naught. Let me get my face back. All right, initial counterclockwise angular velocity omega naught. So usually if it's counterclockwise, that looks like this. And in that case, if you use the curl as the finger, then thumb is the direction of the spin. Okay, that's actually vector. So in a top view, if something rotates like this, then it's gonna come out of page. And usually coming out of page, you choose it as positive direction for rotation, okay? So it's basically they're using standard direction. All right, and sketch graph that could represent this angular velocity function of time t equals 0 until this comes to rest at t equals t1. So it comes to rest at t1. But here you have constant torque, and this torque will be generated, which will be I alpha. I is moment of inertia of the disk, which is not going to change. So this is constant, then alpha is constant. That means omega is right now decreasing. Right now this torque will be negative actually, because alpha will be negative, because that's the opposite direction of initial angular speed. Okay, so omega will decrease, but since it's constant, since alpha is constant, omega will drop linearly. Okay, so we are expecting omega and time, omega drops linearly like this, and this alpha is constant, but it's gonna itself will be negative. Also torque is negative, okay, because torque itself is negative, because alpha is negative, I is always positive number, right? And angular velocity, but be careful, this is t1's right there, and omega naught starts here, and you're gonna stop at t1, so angular velocity has to be 0, so you have to draw a straight line like this. And angular acceleration has to be constant. Basically, angular acceleration is slope of this line, which is negative constant. So probably you'll have to draw like this, okay? Now, magnitude of frictional torque exerted by disk is T naught. Derive equation for rotational inertia I of the disk in terms of the variables, okay? So let's think about how you're gonna relate them. All right, so what I know is you had initial omega naught here, they use omega naught, and eventually this becomes 0, which is omega final, after time t1. And this is basically equation for acceleration, right? So remember, linear acceleration is v final minus v initial over time, and angular acceleration is omega final minus omega initial over time. So here I can say omega final is 0, omega initial is omega naught, and time it takes was t1. So basically alpha is that quantity because this is just 0. But remember also torque, which is R cross F. In this problem you don't have to really worry about that, but this eventually becomes I alpha, okay? And you have alpha right there, right? So alpha is also torque over I, okay? So you can set up this, and you have to use T naught here because this is torque naught. And you're looking for I, so you can just set them equal, right? So here, negative omega naught over T1 equals torque naught over I. Now, you have to be a little careful because torque naught is, this itself is negative value, okay? This itself is negative value. So I will be actually positive value. So what's I? I equals torque naught times T1 over negative omega naught, okay? So you can write it that way. And if I want to say, I want to make side note, T naught is negative and I is positive. Okay, if I want to make sure. All right, now let's look at part C. Did I do? Okay, I want A and B. Let's look at part C. In another experiment, this again has initial positive angular whether not. And at time t equals half t naught, student starts dripping oil on contact surface between axle and disc to reduce friction. Okay, so there's friction gets reduced. As time passes, more and more oil reaches the contact surface, reduce friction even further. So now friction is decreasing and it's changing. So acceleration is gonna be smaller, but it's not gonna be constant. Okay, so angular velocity. So I'm expecting something like, I'll just write here omega, and until you reach t1, it's gonna drop linearly, and then if you put oil there, it's gonna this slope has to be reduced, and it's gonna be even reduced, something like that. It's gonna reach maybe 0 around there, but we don't know that yet. But we can just say this one drops like that, right? So here you can say omega naught, it drops linearly, then it has a smaller slope. So I'll just, oops, I don't like this part because this says steeper. So I want to make a smooth curve like that. Okay. Hey, this because I made this slope too small. Probably it'll be easier if you could make it like boom, then something like that. Okay, that'll be a little easier, I guess. But because the previous question I used slope like this guy, that's why I want you to keep the same slope. Okay, but I think then you'll have to really draw like this. Okay. All right, angular acceleration. This is basically slope of this line. Okay, so until you get half t1, this will be slope constant. But right now, slope of this one is actually changing and close to 0. So this is still negative, but the magnitude will decrease. So it's gonna probably look something like that. Right. I guess I have to reach t1, so I'll just go like this. And still, if you leave that much amount, that means still the angular speed is decreasing. Okay. All right. The student is trying to mathematically model the magnitude torque exerted by axle when t is greater than half t naught. That's when oil was dripping, right? So that means torque has to be smaller and negative, right? Which equation better mathematically model this experiment? All right, let's take the first one. Remember, this t value is greater than half t naught. That means this value will be positive. That means torque is actually getting bigger, okay, when time goes on. So one doesn't work. Second one, when t gets larger, you get bigger denominator, so torque gets smaller. And I don't think they care about positive negative because I think it's a it's a magnitude, okay. So I don't really care positive negative. So I'll say equation 2. And the reasoning is as t goes on, as t goes up, torque goes down, right? Then alpha goes down to magnitude of alpha will go down, okay? Yeah, I have to be careful with this because magnitude of alpha, for example, is like -2 become -1 and -1/2. Let's say this magnitude of that is decreasing, but actual alpha is actually increasing, okay? Because -1 is bigger than -2, -1/2 is actually bigger than -1. Because if you think about number line, it's like -2. You're going from here to here to here. So this alpha itself is actually increasing, but magnitude of alpha is decreasing because if you take absolute value, that's why you have to be a little careful on this sine, okay? All right.